After a few months of hectic summer, the rains are here. The IIT Kanpur campus is green and nature's colors abound once more. With monsoon, however, comes alive the age-old tradition as well. Sunday evenings of guilt-free laziness together with the music of rain splatter, a Bollywood classic on the TV, and some hot simmering tea. Over the years, the world's technologies have changed shape and form, including the TV. Blinking tube lights have turned into LEDs, and televisions have changed from being cubic boxes to flat screens. Why and how did this happen? It has something to do with physics discoveries behind the scenes. Electrons to light. When you switch on the TV, you really just switch on the electrical socket where the TV plugs in. We know sockets carry electric current transported by electrons, but how do these electrons become light? This isn't unusual. If you think about it, we see it all the time in our houses. The protagonist of the light of this puzzle is a class of materials called phosphors. The phosphors, which are different from the element phosphorus, are also called fluorescent compounds because they have something magical about them. When an electron hits a phosphor, the material throws off light. This has to do with the way electrons are arranged inside the materials. When another electron falls on them, the electron in the phosphor becomes excited to higher energies. When they relax back, they throw out some energy as light. Phosphors are thus used to cover the insides of tube lights and fluorescent bulbs. It is the reason we call them white bulbs, CFLs, short for compact fluorescent lamps. Inside the bulb or tube light, one just needs flying electrons or other charges to hit these materials. If you have ever seen an old broken tube light, the powder inside the glass tube is nothing but phosphor. Moving pictures. In a tube light, since we just need the light, we can uniformly coat all the sides with phosphor and whole frame will light up when electron strikes it. But to create a picture on the TV screen, we need a few regions to light up and a few regions to remain dark, the way we can see the landscape of lit regions as a single image. We also need the lit regions to be able to change quickly. So quickly as the picture changes, our brain thinks it's a moving scene rather than a series of still images. Enter a major invention of early 1900s, the cathode ray tube. A cathode ray tube creates a stream of electrons through the tube flowing towards the screen. Imagine electrons as a flock of birds flying in the same direction towards the wall, which is this case of the screen. Which is this case is a screen. Now imagine a bird traffic signal manager that can direct bird towards different points on the wall. We similarly need a way to direct electrons to different points on the screen. If we know how much to deflect them and how fast are they moving, we can plan exactly the location on the screen they will strike. And where an electron strikes, the region will light up, just like the conductor of orchestra. If our bird traffic manager can direct birds to different locations on the wall, we can continuously change the parts of the screen that will light up, creating a moving picture. Magnetic fields. Now, even as we have the stream of electrons, how do we deflect them at will? This is done with the help of magnetic fields. Electrons have charge, and one can move charges using two kinds of forces. Electric fields can make them faster or slower. This is what we see in clocks, wires, and torchlights. Where batteries create the field, magnetic field, however, can do something more interesting. It doesn't change the speed of the charged particle, but it can make them move in a circle. It's like when you tie a ball with a thread, you can pull the ball towards yourself, or you can try to swing the ball around. This kind of force is called Lorentz force, and it is applied by magnetic field. We can use magnetic fields to move the electrons to the location that we are interested in. Thus, we have our traffic police. A bunch of copper wires and coils can be used to create these fields. Such electronic circuits are called analog. While a lot of physics and engineering goes into creating the perfect images that you see on TV, the basic physics is simple. We understand how electrons get directed to different locations on the screen. As they strike various locations, the phosphor lights up. As the TV signal changes the points where electrons strike, the screen changes continuously, playing for us our favorite Bollywood film. Boxes to screen to. With time, of course, physicists discovered new concept, and we didn't need all these coils of wire to move electrons. In 1947, scientists at Bell Labs in the US invented transistor. This device led to a computer boom and eventually semiconductor electronics. Here too, the simple concepts are similar. Instead of phosphor, we have another light-emitting material called gallium arsenide phosphide, which throws out light when electrons go into them. Instead of rays of electrons, we can direct electrons more precisely using electronic motherboards like in laptops. If you are wondering how these new technologies work, that is a story for another day. The reason we could make moving pictures was the magnetic field's ability to deflect electrons. Here, the electrons were moving in 3 dimensions, the same number of dimensions we live in. The dimensions of space is the number of directions in which we can move. For example, if something can move in all the directions, right, left, front, back, top, down, it is said to exist in 3 dimensions. A TV of future may just take advantage of electrons' force to move in 2 directions, front, back, right, left, like an ant on the table. This happens in some particular material, like physicists can make in lab. It turns out there is a big difference in physics between 2 and 3 dimensions. If 2 dimensions, in 2 dimensions, the temperatures are very low, a group of electrons can behave in a funny way. They form what is called a fractional quantum Hall state. Here, effectively, new particles emerge that have just 1/3 of electron charge, and they can move along the edges of the material. Robert Llewellyn, Horst Ludwig, Horst Ludwig Staumer, and Daniel Sui won Physics Nobel Prize in 1998 for discovering such particles. These kind of particles are called anyons. They are completely different from the particles which we usually encounter in 3D, like electrons and photons. Scientists are trying to build a new powerful kind of quantum computer using anyons as their qubits. These machines could be responsible for bigger technological revolution in the future, and not just TVs, but for now we still don't understand all physics of anyons or NINs. ANYONL, the Wolf Prize, one of the most prestigious physics prizes, was given to Janendra Jain among others in 2025 for developing the basic understanding of some of this physics interestingly. Professor Jain, who now lives in US, did most of his early studies in India, including in Maharaja College in Jaipur and IIT Kanpur. If you are inclined to understand some of physics that goes on here, you will need to learn quantum mechanics and condensed matter physics. You can consider taking a course in physics here in IIT Kanpur, where some of us teach future TV. Just like the invention in 1947 of transistors soon gave rise to the first TV, the discovery of particles of fractional charge may turn contemporary TV into something which we can't imagine now. We never know how discoveries in quantum condensed matter physics today will change the world in the next 30 years, but just like the warmth of a hot tea on a monsoon evening, the charms of Bollywood classic and basic physics never get old. Next time you watch an emotional scene unfolding on your TV, don't forget to thank the electrons and the magic of materials working behind the screen. So this article is written by Adeep Agarwal, an assistant professor of physics at IIT Kanpur.